All right, I'm going to introduce Nick Schmerr, who needs no introduction. Nick's a visiting investigator at Carnegie and a frequent visitor. Actually has a mailbox here, and there we go. But I'm going to tell you a few things about Nick that you may not know, even though he frequents Pure Hour and we often have great conversations. He was an undergraduate geology major at Beloit in Wisconsin, where I think he fell in love with geology, and did a number of summer internships, actually more than I've ever heard of anybody doing, 3. He worked with Larry Edwards and Mark Hirschman doing U-series and ICP MS work at Minnesota. And they did a summer internship with Faye here looking at experiments on the Martian mantle. So yes, he played for the other side, unfortunately. And they did a summer internship at Goddard looking at MOLA data. He went on to do a Ph.D. with Ed Garnero at Arizona State, where he looked at upper mantle seismic discontinuities using tomography. To quote from the nice introduction that Casey wrote of Nick's interests, he likes to decipher the formation, dynamics, and evolution of planetary surfaces and interiors, and especially looking at the physical and chemical properties of rocks and minerals and how they're related to the evolution, in particular using seismology as one of his key tools. Nick is, without doubt, one of the few geophysicists I've met who has a good grounding in petrology and who's actually run an ICP-MS, so what can I say? Today he's going to talk to us about how heterogeneous is Earth's mantle, combining new observations from seismology, geochemistry, and geodynamics. Nick?
All right. Can everybody hear me all right? All right, good. I'll bring the lights down a little bit. All right, Steve, well, thanks for that introduction. Today I'm going to talk to you about how heterogeneous is Earth's mantle. And this is a question that I've been thinking about for more than a decade now. Is basically, how can we go in and figure out what's going on inside of Earth's interior and see where the thermal and chemical variations are and what their exactly origins are and where they're coming from. And to do this, we really need to take observations from not just one field, but from a lot of different fields. And so I'm going to bring in some information from seismology, I'm going to attempt some geochemistry, and a little bit of geodynamics to try to put these things all together. So my takeaway points for this talk are, first and foremost, that the Earth's mantle is heterogeneous. I think this is a fairly well-established fact at this point in our interrogation of what's going on in the interior, and hopefully I'll be able to provide you with some more evidence that supports that interpretation. And the way I'm going to do this is I'm going to show you that there's evidence for a widespread seismic discontinuity about 300 kilometers depth that is not part of our traditional lexicon of discontinuities in Earth's mantle. And this is called the X-DISCONTINUITY. And there's several different mechanisms that have been ascribed to this particular discontinuity, but I'm going to show you that the transformation of coesite to stishovite is actually indicative of this particular seismic discontinuity, and where exactly this is, in this case, the Pacific mantle. And the way we get this material into the mantle to actually produce this discontinuity is perhaps through a plume mechanism. Plumes will entrain material from the deep mantle and bring it to the surface, and at some point along that trip, it gets placed into the mantle somewhere else. So the idea is that we can look at these thermochemical plumes, not just a thermal plume, and actually study their behavior as they transport through the mantle and see how they can introduce the chemical heterogeneity that produces this discontinuity that's being observed off the Pacific. So I want to start really, really broad on the big picture. And starting at the formation of the solar system, I think, is a good place to go. Because, we don't want to go to the Big Bang. That's maybe a little bit too broad. But the idea is that the formation of the solar system took place as essentially you have formation of the solar nebula, and as that solar nebula condensed, you had a thermal gradient across it, and you essentially introduced different materials within that nebula because the sun blazed volatile and whatnot. And what this does is it basically creates a variation in the amount of building blocks that are available to build the planets that we have today. So you have these early magma oceans and impact and accretion of all these different materials, and they differentiate into different bodies. And so what that gives us is a diversity of worlds. And I'm going to focus primarily here on the silicate bodies that form the interior of the solar system. But there are possibilities for others. So just to kind of take you on a quick tour of all the different objects, we have undifferentiated objects like comets, which are the mixtures of volatiles and rock. But these come from the outer solar system, occasionally wander their way into the interior of the solar system. We have asteroids, which are these big rubble piles, materials, but they're not really differentiated. As we move to larger objects, we can find things like the asteroid Vesta or Ceres, or these other objects that were recently visited by the Dawn mission from NASA. And we think that these are partially differentiated, i.e. they're segregated out of the core. And then as we move to even larger objects, like the planets and their satellites, we see a huge diversity of interiors and material properties of these planets and surfaces. And so, if we put those onto a spectrum, in this case here, just for terrestrial bodies, we have these asteroids, the rubble piles that have low differentiation. And as you move to the right, you basically start finding things where you segregate out a crust, you have mantles, you have cores, and in some cases you start to develop atmospheres and hydrospheres, where actually able to capture volatiles and hold them at the surface. And as you move to the larger objects, something else happens, is you start to get dynamics in the interior. For some of the smaller objects, we essentially cool them off and they create a stagnant lid. You don't see a lot of surface dynamics that are taking place. But as you move to larger objects, you start to see things like perhaps episodic lids. It means you have maybe a period of overturn in the history of a planet. So, or as you look at Earth, you see a mobile lid where you have constant recycling on the surface. And then as we get to these really, really large objects, for example, the exoplanets that people have been finding around other stars, we start to become a little bit less sure what's going on. Maybe these are stagnant lids that are heat is lost through heat pipe transport through it, or maybe they're plate tectonics worlds. We don't know. And of course, there's examples of these that we have for the solar system, so you can kind of guess which is which. But the one I'm going to focus on primarily today is Earth, which is in the mobile lid regime, and it has sort of a whole bunch of different dynamics that could be changing what we would think of as sort of the initial differentiation of that world. And I would be remiss if I didn't point out that this is just for the silicate worlds. You can have a whole variety of different objects that would be formed if you were to, say, deal with ice or hydrocarbons, and in fact we have examples of these in the outer satellites. But unfortunately I don't have time to dwell on that today, but it's a very interesting thought experiment to figure out how those worlds would work. So this idea that we can stir the interior of a body by introducing convection or changes in the interior, transport of heat. On Earth, we think that we have essentially a convecting mantle. So this is a simulation from Alan McNamara, where he's basically introduced a heated from below rheology that then starts convection. So you have these downwellings in blue, which are supposedly cooler, that are equivalent of what we would call subduction zones on Earth. And you have these hot thermal upwellings, which are plumes. So you might get a hot spot formed above these things. And so this is for purely thermal convection. As you can see, it's stirring the interior. Now, if we think about a case of where we have thermal convection combined with compositional convection, so you have two different materials here segregated from each other initially in the model, and you let that convect, so you can see the thermal field driving this sort of mixing in of this chemical composition. Now, this is just for a theoretical two-layer model, but as you can see, as you drive that convection, you start to mix in this lower layer. As the colors evolve from purple to sort of a greenish, you're getting sort of more homogeneous, but you still have quite a bit of heterogeneity that's left over from this convection. So we haven't completely mixed the mantle, so to speak. So we think that some of these processes might be going on inside of the Earth, and they take the form of subduction through plate tectonics. As far as we know, Earth is the only object in the solar system with plate tectonics currently. There may have been plate tectonics elsewhere on the other planets in the solar system. This is segregated the materials out into continental crust, which is fairly ancient relative to the oceans, which are fairly young. You have creation of new crust at the mid-ocean ridges, and then destruction or recycling of that material back into the interior at the actual subduction zones. This is kind of a whimsical cartoon of how subduction and plate tectonics works. You have these gears driving plates into the mantle, and then this plume juice being burped out at the mid-ocean ridge. I just had to throw that up there because it's April Fool's Day. I think this is the more textbook, literally, interpretation of what's going on in a subduction zone. So you have this oceanic crust and the depleted lithosphere beneath it being brought down. You maybe have some remelting going on. It's producing volcanism. You have upwelling at the ridges. And not shown on here is you probably have hotspot volcanism coming through the interior. This leads to a lot of questions. Well, if you have this material being recycled back into the deep Earth, how well mixed is Earth's interior? If you've taken this stuff and completely mixed it back into, do you get a perfectly homogeneous mixture? Or is it heterogeneous? Are there changes from one spot to another in both depth and location? The other question is, well, how has this changed over time? Was the early Earth just layered and then it got mixed, or is it sort of had mixing going on through all the history of the Earth? We don't really know. And how and when did that actually begin? That's another big question we don't really have an answer to. So we can kind of take those questions and answer them, or ask more questions on top of them. Well, where is the mantle actually heterogeneous? That might give us some clues as to how we can go and answer the previous ones. And then with the scale, it is mixed in. If it's mixed in at the scale of subduction zones, or if it's mixed in at the grain level, or if it's mixed in at thousands of kilometers, we can go in and look at these signatures and figure out maybe what it's telling us about this sort of heterogeneity that's taking place inside the Earth. So when we ask this question about how mixed is the mantle, this is where we have to turn to the rocks. And this is something that I've always said that we should take things back to what we can physically observe and then try and make those comparisons. And so on Earth, we have basalts that are erupted at ocean islands. We have basalts that are erupted at mid-ocean ridges. And we can go in and look at the isotopic systematics within those rocks and try and understand their origins, where these melts are derived from in the mantle. And if we look at mid-ocean ridge basalts, and this is, I'll walk you through this, is showing you a lead-lead isotope versus the strontium. So you basically have the primordial lead 204, which is formed at the beginning of the solar system along with the planets when they were accreted. And then you have this radiogenic lead that's been produced by decay of uranium-238 over time. So you would expect over time, if you had uranium present, that the amount of 206 would increase over time. So therefore things would get, you would be introducing more and more of that 206. So for the deep mantle, you would expect 206 to not really be present, because uranium is an incompatible element. It would go out of the mantle and go sequestered into the continental crust and not basically not be present in the lower mantle. But what we do find is if we go look at ocean island basalts, is we find some ocean island basalts are actually enriched in this amount of uranium, which implies that we've had some sort of recycling. That uranium has come back from the surface back down into the interior and allowed to age and introduce its daughter isotope back into the system. So the interpretation is that maybe we have some sort of recycled component of subduction down in the deep mantle. The ocean island basalts themselves sort of segregate out into these different fingers, which are pointing towards these regions where you actually have recycled sediments coming off of the continents or off of the sediments that deposit on top of the oceanic floor. So it suggests you have this variety of different materials that can be mixed back into the mantle. And if we just look at warbs themselves, they sort of fall down here towards the direction we would expect things to be more depleted. So you have sort of a mixture of different things that are going on, both an recycled, enriched component, and then you have this sort of depleted component in the mantle. And so when we think about where these heterogeneities can come from that we see in the rocks, people have come up with a whole variety of different mechanisms for what these reservoirs might be, where you've sequestered these different elements at so that they can then be sampled by some sort of dynamic process and brought to the surface and put into the rocks. And so here are a bunch of cartoons from Paul Tackley's earlier this last decade science paper where he's suggesting origins for these different geochemical domains, isotopic domains. And so, you've got this idea that the very lowermost mantle of the Earth is all this primitive material. I've tried to color things so that they would match up with what Paul has put into his diagrams here, with ocean island basalts bringing up the sort of mixture of these different things, subduction zones bringing down mid-ocean ridge basalt into the mantle, and then there's all kinds of possible ideas. Maybe you have subduction getting all the way down to the core mantle boundary, and you're enriching on the core mantle boundary with this essentially continental material that then ages and produces. You bring uranium down with it, it ages and produces this 206 lead. And then it gets sampled by the plumes, or you have maybe some mixture, like plum pudding model, where you have big blobs of this primitive stuff. More recently, people have talked about these big piles of material that sits down at the base of the core mantle boundary. Maybe you have topography on those. There's a lot of different ideas. And the question is, well, how can we go and test these different ideas? I mean, we can only look at so much with the rocks that we see at the surface because we're sampling only things that erupt at the surface, but with another tool, i.e. seismology, we can go and actually image these things and see if we can find what one of these models might really fit what's going on inside the deep Earth. So this is where my tool of seismology comes into play. So this is a 3D wave propagation simulation of seismic waves traveling through the interior of the Earth, and some of them are reflecting off of the core and bouncing through the mantle and traversing the core. And just to give you an idea, seismic waves sample the entire Earth. So we can get creative and actually find ways to measure these parameters. So you're looking here at profiles of the shear velocity, the P velocity, and the density of the Earth. For a standard reference Earth model, this is PREM. And there's actually a meat product sold in Canada called PREM, which I think is fantastic. You know, we know the Earth is made of processed spam-like material, I suppose. I hope not. Be very yucky. But what we see here, you basically have velocities that increase with depth. We note that there's a core, because you lose your S wave velocities, and this core is fluid. We see a large increase in density. So with seismic waves, we can actually go in and study these properties. So the canonical method that people talk about, usually you hear about, is tomography. This idea that you basically go in and do a CAT scan of the Earth with multiple stations and measure the relative changes in seismic velocities from point to point inside the Earth. If you look at one of these models, this is an example from a shear wave model from your own Ritsema, where you basically take slices in depth. So we're just moving through to the core mantle boundary down here. This is the surface, and then you move down in depth. You see these reds and blues. The reds indicate places where you have low shear velocity, and then the blues indicate where you have high shear velocity. And you start to see some features that pop out at you. For example, near the surface, you see these big areas of blue that correspond with where the continents are. The continents have high velocities beneath them. And if we look in cross-section, we can see a few features in more detail. So here are your continents, for example. This is going through Africa. But underneath, say, a subduction zone, so this is Japan right here. So there's Japan. You see these big blue sheets. Those are the subduction zones. And then intriguingly, as you look almost to the base of the mantle, if I go back one, you see these big, large, low shear velocity provinces, and I've just used the actual very unwieldy acronym, large low shear velocity, or LLSVPs. We just call them large low shear velocity provinces for simplicity, so you don't have to remember the acronym. But these sit at the base of the mantle, and they're probably some of the lowest velocities on the planet. And if you look at these things in cross-section, you basically see you look at these big blobs that sort of rise up off the base of the mantle. And so a lot of interpretation that's been put into the tomography is that these things are thermal. So these things are hot and these things are cold. But that's not really the entire story. There's a trade-off between composition and thermal effects in terms of creating seismic velocity. And that's where I'm really going to take you guys in the rest of this talk. That's when I'm getting into this in detail. So we can create a theoretical seismic profile through the mantle. This is from mineral physics, and study the effect of temperature and composition on those seismic velocities and densities. So what I've shown here on the left is you have various temperatures. Blues are cold and reds are hot. As a profile of depth, this is through the upper 1,000 kilometers of the mantle, and then here's just the relative variation on that. And if you look, you see that the seismic velocities are high when it's cold and they're low when it's hot. But if we sort of change our frame of reference now and go and look at constant temperature and then vary the composition, so this is a variation in the amount of basalt, say, mixed into the mantle. So you can think of it as two members of Harzbergite, which is this depleted mantle, versus a member of basalt, which is this enriched material. And you just start adding a little bit more basalt, about up to 40%, and you see that the larger fractions of basalt are actually fairly high velocity, while the lower fractions of basalt are low velocity. So that there's this sort of trade-off between the two, the composition and the thermal effects. But what should really stick out in your on this particular diagram, and I bet most of you have spotted this, is this big change that's introduced where you have these jumps in seismic velocity and seismic discontinuities. If you look at the thermal effects, you see that they get deeper, or get higher, this particular seismic discontinuity. And there's not a huge amount of change in the depth from the compositional effects, but it does change the velocity contrast across the boundary. And so these are all related to phase transitions in the mantle. You have reorganizations of mineral structures as you go to higher pressure and temperature that causes them to get more compact. So by being more compact, they typically have higher bulk and shear modulus, so you get a higher velocity. And we can actually study those with seismic waves and use them as a very sensitive indicator of the variation in thermal and compositional effects inside of the Earth. And this is something I've spent almost a decade working on. So just kind of want to walk you through how we do this. So if we look at a phase diagram of this is temperature here on the x-axis and pressure here on the y-axis. As we look at sort of the evolution of a mantle composition through pressure and temperature space, we see various phases coming in and out. So these are all the phase changes. You can look at this in terms of the bulk rock. So this is for a fixed temperature, just basically taking a slice through this model and looking at where the phases are stable. So you see the predominant component of the mantle, olivine. I've shown a nice little xenolith here of it from the San Carlos olivine. It transitions into this phase Wadsleyite at about 400 kilometers deep, which forms the sort of classical 410 kilometer discontinuity. There's another phase transition from the Wadsleyite to the ringwoodite structure. That takes place at about 520, and then we have another one around 650, 660 kilometers deep, where the ringwoodite phase transitions into magnesiolustite and then the magnesium perovskite. And at the same time, you also have this component of the garnets, which go through much more gradual phase transitions. So if we then translate those mineral phases into seismic properties, this is what we get. You see basically these jumps in density and the compressional and shear velocities at about 410 kilometers. So there's our 410 kilometer discontinuity. There's a very weak change at about 520, which is this phase transition here, and then the 660s. So the phase transitions can tell us quite a bit about what's going on inside the mantle. But how do they do that? If we look at their sensitivity to temperature and composition, you can get a better feel for this. So this is just a simplified phase diagram for the various olivine phases over temperature and pressure space. If you pick some mantle temperature, some profile of mantle temperature, you see that the 410 and 660 basically get fixed at some depth based upon the Clapeyron slope, which is the change in the slope of this boundary through temperature-pressure space. And if you move to a mantle that's a bit colder, for example, you see that the boundaries then essentially move away from each other. You have a shallower 410 and a deeper 660. This is the classical thickening of the transition zone, as we call it, for all of these different olivine minerals that we can then use to say, oh, if the transition zone is thicker here, then it must be a little bit colder. As we then sort of change it around and think about how composition can play into this. So here's a phase diagram where we've got a join between the magnesium member of olivine and the iron member of olivine through pressure space. If you pick some composition of the mantle, in this case about 0.89, which is the typical number people use, you see that the discontinuities fall at a given depth. And then as you sort of change that composition, they move around. So here's a way you can introduce topography on the boundaries by simply changing the composition. So there's this interesting mix of various effects that we can put together. So for the Earth, how do we sample this? So we have a variety of seismic phases that bounce around and reflect and convert off of these discontinuities within the Earth. They're sensitive to these elastic contrasts and the sharpnesses of the discontinuities. And we can go in and use those to sample their depths and their sharpness and see what exactly is going on in each of these individual interfaces. And so if we do that and then make a histogram of all the detections people have made over the years, this is an example from a review paper by Arwen Doyce, and plot this up in histograms, we see the classical 410, 660, there's a few detections of the 520, but there's some interesting outliers. There's an 800 kilometer discontinuity that seems to pick up out of the noise. There's these things around 300 kilometers deep, and then there's this 220. So the question is, well, what are these other discontinuities? They aren't really predicted by the phase transitions that we see in these old Earth models. And I'm going to focus today on one of these. This is the 300. I've sort of circled the depth here that it's found at. Here's a map of where it's detected. You have sort of regionalized, wherever it's sort of shaded gray, you have detections of this discontinuity. You can see it shows up perhaps beneath subduction zones, maybe a few hotspots in continents. This is not a phase transition that is predicted by the pyrolytic mantle.
Sorry, Nick?
Sure.
How are you defining discontinuities in that plot? Because, I mean, if you're focusing on the 300, there are other areas on that plot that are higher in terms of frequency that you haven't applied this discontinuity.
So you're saying like these areas, or are you thinking?
Yeah, or the shallow.
The shallower
What's
ones.
the definition?
So you can look at the shallower ones by themselves. You can look at them all together. It's just a sort of a question of what sort of depth shell you're interested in that particular study. The way you do these things here is, I'll get to the details of that in a few minutes, but like you can actually just survey through depth and see where there's a reflection coming from one of these various seismic phases. And if you plot that up, you'll get this sort of.
Right. I know where the data come from. I'm just asking why are you calling that the 1 and 2% at 300 a discontinuity and not the 2 to 3% at 50 to 100
Well,
kilometers?
you could go and survey this different region here and see if there's any consistency to it. The fact that there's a lot of variability in where these peaks are just suggests that maybe there's a large variation in the depth of the boundary. I mean, we think about the 410 and 660 as relatively confined to one depth, but maybe there's multiple boundaries here that are just sort of stacked on top of each other. There's a lot of complexity in the uppermost mantle, which is why we don't have singular discontinuities for these various boundaries. In fact, there's some places where you might have a lot of topography on the boundary, either from thermal effects of a cooling plate or other mechanisms that would give you a sort of a range of depths, not necessarily a nice singular depth that you see from some of these other boundaries. So the mechanisms can change from different boundary types. So discontinuities aren't always from phase changes. You can sometimes get them from mechanical properties. The crust mantle boundary is an example. It's not a phase change, it's a composition change in the interior. The core mantle boundary is another example. And then if you think about the crust depth, for example, it varies quite a bit from location to location. In fact, if you were to plot it up on this histogram, you would see a bimodal peak. You'd have the oceans, and you'd have the continents with different crustal thicknesses. So you get a range. I don't know if that answers your question, but there's a lot of heterogeneity that can go into these things. The reason why I'm focusing on the 300 is it's one that's had a lot of different mechanisms, and so that's what these are up here. Is you've had a variety of mechanisms proposed for this particular phase transition, and what those are speaks a lot to the heterogeneity that's present in the mantle. So, for example, hydrous phase A. This is a transition that we only find in subduction zones for the most part. It's only stable below 1100 degrees C. So you wouldn't expect to find that everywhere. But if you were to survey subduction zones, perhaps the subduction zones are contaminated by this signal. Versus a transition in the pyrite seeds in the mantle from this, I'm trying to remember this, either orthorhombic or then to monoclinic, I can't remember the exact mineralogic reorganization. This can introduce a discontinuity about the same depth. And then if you have a little bit of free silica mixed into the mantle, you can get this coesite to stishovite phase transition. And I'm talking like 1% coesite to stishovite. It has a huge change in its bulk and shear modulus, so it can actually produce a discontinuity with even a fraction of 2%. And we can actually investigate this by going in and looking at the structure of these continuities. So the key questions I'm going to ask about the X, is this a ubiquitous feature of the mantle, or is it just a regionalized feature? I think this is very important for determining if it's a regional feature, perhaps there's only something in that region that produces it. But if it's ubiquitous, then we have to have a revision on how we think about what's going on in terms of the mantle, in terms of the discontinuities that are produced by phase transitions or other mechanisms. What's its character, what its seismic character is, what its sharpness is, its depth. And then what are the models that have been proposed that are consistent with those observations? And then, of course, how can the X tell us anything about heterogeneity? So just to remind you, the X is this 300-kilometer discontinuity that I showed in this previous slide, which has been somewhat enigmatic. So if we go back to this plot of where it's been found, you'll notice a few things. These are sort of strung out into what I would call corridors. That's because of the seismic phase that's used as essentially a reverberation in the mantle, and it only occurs along one given corridor. We've not actually gone in, interrogated a large region of where this boundary might be to see. We've never really looked here to find it, so we don't know if it's there or not. So the assumption is it's sort of showing up only in given locations. But we really need to interrogate it with a whole bunch of different regions. And we can do that. We have this really amazing amount of seismic stations out there here on Earth. All the red triangles are existing or previously existing seismic stations on Earth. And this isn't even the most recent map. After we fill in TA, the US basically just turns pink because we've got all these triangles across it, and pretty soon Alaska is going to be the same thing. And this lets us go in and really interrogate a lot of areas and study what's going on with various boundaries. And so the way I'm going to do this for the rest of the talk is using these underside reflections. So you have an S wave that reflects off of the crust at the center of its path, and then is picked up at this station, like one of the various seismic stations in the previous plot. And if we zoom in on this region where it's sensitive to what's going on with discontinuities, you get reflections off the 410 and the 660, and we can see those. And you can also get this reflection off of the 300 if it's present. And so this gives us something that looks like this. You have an SS wiggle here. I think this is one of the few seismograms I'll show in this talk, but you have an SS wiggle here, and then preceding it by a few hundred seconds, you have little wiggles that are being formed by the reflections off the discontinuity. So we call these SS precursors because of the fact that they arrive before the SS phase. And so the SS precursors are really nice because they let us go and sample large regions and vast areal extents. And this is just showing a bounce point sampling density plot for the SS precursors. So anything above basically green here is pretty good sampling. And if you'll see, you can kind of see the profiles of the continents here. The Pacific Basin itself is really, really well sampled. So that's the region I'm going to focus in on this, but of course we want to go global. But I just wanted to do a test study here to show what we can do with the X. So here's a little bit of seismology technical detail. If we take our SS waveforms and we align them by epicentral distance, and then we stack all the data that share the same epicentral distance together, we can basically recreate what the seismic wave field looks like for that SS phase. So here's your SS right here, this bright blue thing with red side lobes to it. And you see these other phases that line up. These are the precursors from the 410 and the 660 kilometer discontinuity. This is the S and S diffracted phase and some of its multiples that reflect with discontinuity. I'm not going to talk about those today. But if you look at this in terms of a travel time plot, you can basically see where the predicted time for SS is and where the predicted time for the precursors are. And the one we're interested in falls just a little bit above the 410. This is the S300S, sort of around that range. So we select all the data that fall within that time window and be careful about these interfering seismic phases that can masquerade as another boundary. You don't really see a coherent interface show up in these global stacks. And that's probably because there's quite a bit of heterogeneity on this boundary, which makes sense from what people have seen in the past. If we plot up the previous plot that shows where all the variations are, and then use that to show both the depth that they've measured, so that the blues and the light blues are basically showing the variation in depth from various studies. So you can kind of see this regionalized nature. The hot spots are shown as the yellow crosses, and then the plate boundaries in red here, so you can sort of figure out where the plates are. And then the sizes of the various symbols are scaled to the shear velocity contrast, which is actually the shear velocity impedance across the actual boundaries. There's quite a bit of variability in that as well, to about maybe 7 or 8% in some of these really outlying crosses. If we go in and then take a global sort of data set that samples the whole Pacific, we can make stacks of the seismograms to bring out these discontinuities. So here's a couple of examples of stacks of SS precursors where we detect this discontinuity at about 300 kilometer deep. So you see the 410 shows it really nicely, and then you have something about 278, which is this little peak here, and then this one at about 200, 274, 310. Now if we put those onto a map, the entire Pacific lights up. Now the impedance contrast that's present in each of the individual locations varies quite a bit, but compare it to the previous location map and then this, you get a huge number of hits. And this is just for the Pacific. You might have focused in on the Pacific. So what is this telling us about this discontinuity? So we can look at it in terms of a histogram. So this is depth. And in this plot right here, we're just trying to see if there's coherency across the plate as it ages. You see that this shallower one basically shows up in the younger ages, and then we have this sort of mishmash of discontinuities throughout the Pacific. We're joining all the data across the plate into a single profile, so there's going to be some heterogeneity. But if we look at this in a histogram sense, we see this L, which I'm not going to focus on today, but like Diana asked, so there are other discontinuities that we spot. But there's this other sort of more distributed distribution of reflectors from around 230 to about maybe 350 kilometers deep. And I'm going to call those are the X. And if we look at the impedance contrasts that are present in those, we see sort of about 1 to 3% shear impedance, maybe with a couple of outliers of the high end tail. And this is sort of where our sensitivity to the discontinuity drops off, basically because below our noise level, and then everything's weaker than that. And so we can take those observations now, this variation in depth and impedance, and compare that to several mineral physics models for what's going on inside of the Earth. So we can test the cosite to stishovite phase transition. So we have this, the blue line here is basically showing you the depth and the pressure sensitivity of the cosite to stishovite phase transition from about over temperature. And we can do the same for the transformation of the pyroxenes. And we can basically rule out the formation of hydrous phase A as the primary mechanism for producing this discontinuity, purely for the fact that it's found over most of the Pacific. There's clearly not 1100 degrees C across the entirety of the Pacific Mantle outlier. But if you look at the variation in depth that we see in these histograms, you have basically the shallowest boundary versus the deepest boundary gives you an idea of what the temperature shift you would need if you just had one of these phase transitions producing the discontinuity. You can do the same for the final pyroxene one. And this is ridiculously large temperature change. We're talking about 1000 degrees C across the mantle for these. And this isn't very satisfying. Is it one discontinuity that's producing a huge amount of lateral heterogeneity? It doesn't seem to make sense. So the question then becomes, well, what if we had two discontinuities that were playing together and maybe trading off with one another in a way that we could actually produce two different slopes? And so one idea that's been put out there more recently in the past 10 years or so is that perhaps the mantle is a mixture. You have basalt and Harzburgite coming down with the plate, and this stuff is getting mixed back into the mantle. Now, if that mixing is complete, you have what we call the equilibrium assemblage, where you'd only stabilize this pyroxene reorganization into one discontinuity. And at very high basalt fractions, where you have basically just mid-ocean ridge basalt by itself, you'll have the cosite to stishovite phase transition. But in the case of a mechanically mixed mantle, where you have two phases existing, sort of rheologically mixed together mechanism, you can actually have both. You can have both the final pyroxene and the stishovite phase transition. When you put those together, it actually solves a couple of our problems. The first one being, we have this large variation in temperature. If we have two discontinuities that are trading off with one another, then perhaps that reduces the temperature swing that we need. And it also explains another thing. We have this very high impedance contrast observations for the X discontinuity. The question is, well, how do you get that? Well, the cosite to stishovite phase transition can actually explain that. Now, so if you map out in those mineral physical models I showed earlier what the impedance you would expect from these discontinuities look like, you see that as you go to higher and higher amounts of basalt, you start to get a stronger and stronger, this is impedance here in color, a stronger and stronger X discontinuity. On the other hand, if you start going to higher and higher fractions of basalt, you start moving away from this low final pyroxene to high final pyroxene phase transition. So it's a way to explain why we have these sort of high end numbers out here, but also at the same time we still have a variety of sort of lower end numbers as well. It's all sort of consistent with the actual predicted impedance contrast that we would expect. So this helps us with the temperature problem. It also gives us a way to maybe go in and map where this impedance changes overlap is taking place in the mantle. And this is where we get a little bit more technical, is we can take those mineral physical models, create synthetic seismograms for them, and then go in and compare it to our observations of depth of the boundary and then the amplitude of the boundary, and figure out what is the best fitting model in that sort of mineral physical database that describes the observation. So we do this by essentially finding a misfit between the synthetic and the waveform, and then calculating a statistical parameter that lets us evaluate if the model is a good fit or not. We want to minimize that misfit between the two, and that gives us a map of where we think temperature and compositional variations are coming from all these seismic observations. And so let me just skip to this next slide for clarity. This tells us something about the mantle. So if we look at the variation in temperature now, I have to point out that the variation in temperature is very sensitive to the depth of the discontinuity, and the depth of the discontinuities, as we look at them in the mantle, need to be corrected for structure that's around the discontinuity and the crust. And so our depth measurement is only as good as that correction. So if our tomography model is incorrect, we might be mismatching the depth a little bit. So that gives us a little bit of weird perturbation around temperature. But in general, we see maybe a plus or minus 300 degrees Kelvin variation within the mantle, with some features that make sense, like subduction zones, and some hot thing that isn't necessarily below Hawaii, but it's there. If we look at the variation of composition that comes out of this, we see this is the basalt fraction that would be mixed in. We get about 0.2 to 0.3, which is fairly close to our exploitation for peridotite in the Mantle, about 0.18. There's a big spike there, and that's the vast majority of the areas are close to peridotite. We also see this big tail of regionalized enhancement, where there's perhaps a higher basalt fraction in the Mantle. And so this is perhaps indicative of maybe this eclogite component. So I say eclogite. Really, basalt, when you take it to high pressure and temperature, becomes eclogite. So people have talked about, well, how do you get this eclogite in the Mantle? Why would you have these sort of regionalized enhancements of that particular material? So where is it coming from? So the first hypothesis I'll look at is that we have a deep mantle plume source. This is something that's been suggested to explain the geochemistry of the Hawaiian hotspot. So you have these two different trends. You have the Kea trend to the north and the lower trend to the south. And people look at where these different compositions plot in this geochemistry diagram I showed earlier. And so the interpretation of the Kea is it's something that's more depleted, and the low is enriched by some sort of recycled component. And the working model is that you have the lower trend is essentially sampling something from the deepest mantle, in this case these large low shear velocity provinces, and bringing it up to the surface, and the Kea trend is sampling basically normal mantle. So the idea is the prediction would be you have enriched material to the south and depleted material to the north. So you'd probably see an enhanced X to the south and a weaker X to the north. And if we look at the data to make that comparison. So first off, where is the large low shear velocity province? This is a tomography model showing that. If we take a bunch of cross sections across Hawaii's flow pattern here and look at where the actual shear velocity varies versus where the basalt fraction varies, we see this trend. Essentially to the north, you have high velocity that then sort of drops off to low velocities, and then for the composition, you have sort of basalt enriched that drops off to sort of the more standard values. This seems to fit this model all right. There's also been a number of observations people have done in other hotspots where they see similar north-south trends, and those aren't quite as clear. I mean, you've got basically things that are sitting right within the large low shear velocity province, but not necessarily corresponding to a north-south variation. So I'll come back to that in a minute. The question is, of course, if you have this variation, how do you get it there? How do you get it to 300 kilometers deep? If we think about these classical plumes, thermochemical plumes, as they're sampling something deep, they come out as this very narrow neck up to the surface, and then they sort of pancake out and produce the hotspot volcanism. But nowhere in between do you really make anything more than that few 100-kilometer wide anomaly. And we're seeing things that are spanning thousands of kilometers. So there's a sort of a disconnect between this model and the scaling of what we would expect to find in the mantle. We also have thermochemical models that people have done for geodynamical convections. And these show you can get quite a bit of, this is the thermal field, this is the compositional field, and these are the expected velocities. You see a bit of mixing going on in the upper mantle, but nothing that really sticks out as very large scale. So a revision to that hypothesis is that perhaps upwellings don't necessarily go straight through, but perhaps as this thermochemical component can actually introduce some stalling or stagnation at various boundaries within the Earth. And this is stuff that a work that Max and Balmer has been working on, is where he's put thermochemical anomalies, in this case a large component of a mafic material mixed in with the plume, and looked at the dynamics of it. If you have this mafic component, it's actually going to be more eclogetic in its composition, a little bit denser. It's still hot, so it's able to ascend through the mantle, but if you cool it, it's actually a little bit denser. And as you move across the 410, you actually get a little bit of a crossover where the eclogetic component here, sort of shown in shaded in brown on top of the thermal profile, stalls out and creates this pool just above the 410. And the way he can maintain in this pool the zonation that we see in the Kea and the Loa trends is actually the pool isn't perfectly mixed, and you might get like little streamers that come up off the side that have slightly different variations in their eclogetic component. And so you can still get this Loa and Kea trend from this kind of model. And so his proposed idea is this: you basically have a plume coming out, creates this eclogetic pool, with then shallows out and creates this thermal pancake essentially at the base of the lithosphere. And this is in agreement with people who've seen in tomography, where you have this large, low shear velocity here, sort of at the base of the top of the transition zone, sort of corresponding to Hawaii. And so this is one possible mechanism in which you could introduce heterogeneity at depth. And note that this is around where the top of this thing sits, is right around 300 kilometers deep. And the nice thing about this particular model, it also predicts another feature that we see with reflections, and this is this sort of enhanced Gutenberg discontinuity that sits at the base of the lithosphere in Hawaii. I just kind of threw that in there because it's nice that this model can explain several things simultaneously. So how does this compare to the observations? If we go in and focus in on Hawaii, this is a cross-section from the specific rise to the curl subduction zone. If we look in Hawaii, you see this strong enhancement of the impedance of the X right downstream of Hawaii. And the mechanism for that, this movie will play, there it goes, is you have, this is a movie from Maxine, basically showing this upwelling. Here's your eclogitic pool. And some of that material, the smoke you see coming off of the plume there, is this dense component that's sinking back into the mantle downstream of the plume. And this would actually be the source of this enhancement. You've got this eclogenic material going in, it's increasing the basalt fraction, and will let you have this cosine-distichorite phase transition. And so the proposed model is you essentially have this downflow from the upwelling of the plume that would create this hot eclogenic pod, if you will, that then cools over time, which enhances the X and gives us the signal that we're seeing in the Earth. So I'm getting close to the end of my time, but I just want to point out that there's a relationship of this structure not just to the X, but also to the other discontinuities that we see. If we look at, this is for the 300-kilometer discontinuity X. We look at the actual velocity and density contrast across the 410 and the 660 for the same location. So this is basically the same exact profile. Now you're just looking at the variation in shear velocity contrast and density contrast. Shear velocity is in red, density is in white, and then the p-wave velocity contrast is in blue. This matches up pretty nicely with Maxine's predictions as well. You have plume upwelling here right around the axis, and you're introducing this denser residual anomaly downstream of that. That is actually something that's hot, lower velocity sitting on top of the 410. It would enhance the velocity contrast there, it would reduce the density contrast. So it matches up with the model. Now there's some interesting things going on at the 660 which might tell us about the fate of this material. It appears that the density contrast at the 660 is much higher here than it is elsewhere across the Pacific. So there's some intriguing correlations that are happening with these two different types of data sets along with some of these geodynamical models together. So to summarize all of those observations together, we've taken a seismic interpretation along with some geodynamical modeling and some insight from the geochemistry, and we can take one of Tackley's models and maybe Photoshop and Illustrator up some possible alternatives of what could be going on. In the suggestion here, you have some primitive anomaly bringing things up from depth, and those are being stalled out in the upper mantle, and you see these essentially pods of eclogenic material that get mixed in. You could have a mixing in elsewhere. I haven't really addressed that. That might explain some of the things you don't see, or do see the X-discontinuity away from plumes. I would argue that plumes are a great way to introduce this chemical heterogeneity into the upper mantle in light of these new models that incorporate all the different effects. And the next steps really are going in and doing a global map of this discontinuity to see if it actually shows up beneath all the continents or if it's really weak against some other locations. We also want to go in and look at the story from other seismic phases, including the P waves, to see if we can do the actual compressional contrast as well. That tells us something more about what's going on. And then translating some of these dynamical models into not just movies and pictures of temperature fields and composition fields, but predictions for the actual seismic properties of the mantle. And so, since I have a little bit of time left, I want to talk about the implications of how we can use this discontinuity elsewhere, not just Earth, to think about thermal and chemical variations in other planets. So, for example, Mars. So, if we think about this sort of scale that I showed earlier of differentiation, you kind of think Mars sits somewhere around down here. We have maybe a stagnant lid. But in the past, Mars may have had an episodic lid. It may have had an episodically dynamic lid. There's some evidence from, if you look at the magnetics of the surface of Mars, we see these bands in the southern hemisphere that some people have suggested might be related to subduction. So if this is the case, Mars may have had some mixing going on, maybe introduced some of these chemical heterogeneities inside the interior. In fact, it may just be a primary feature of the deep mantle of Mars from the differentiation of the actual magnetic ocean. Fortunately for Mars, we're going to have a seismometer there in 2 years. So we're going to be actually able to go in and test some of these ideas. So this is the InSight mission. It's actually going to put a seismometer, a heat flow probe. It's going to be measuring the star tracker that looks at the wall movement of the planet. And this will be here in 2 years and sending back data for about 2 Earth years. So here's a great opportunity to start thinking about how we can do this type of seismology elsewhere in the solar system. And so the way we do this is we can take this is something I did with Faye many years ago. You can take these Martian meteorites, the stick meteorites. This is an example of a Schmerr, and construct a mineral physical model for what we think is going on in the interior. Now it's highly theoretical. We don't really know what's going on in the Martian interior. We can actually measure a lot of these boundaries. But we can take the composition and work it out for high pressure and see what seismic velocities shake out of that model. And lo and behold, you predict some discontinuities that should show up in the Martian mantle. And these would be things that we can image with seismic waves. In terms of the X, I know that this doesn't show any of the phase transitions that would be associated with the X, but if we had the same kinds of heterogeneities mixed into the Martian mantle, we'd be able to produce this X. So if one of the primary features we see from like a seismic reflection experiment on Mars is a relatively shallow boundary around 800 kilometers deep, maybe this is an X. It's showing you that there's some sort of compositional heterogeneity going on in the interior of Mars. And so just to give you an idea, we don't really know what the thermal history of Mars is and how the core is affected. This is a nice set of simulations from Thomas Rudis at DLR now, where he puts in the phase transition relationship. So for a relatively small core, you just bring right at the base of the mantle, and then lets them convect and sees how that basically thermal mantle evolves over time. And this is a thermochemical convection, but it can kind of give you an idea if there was chemical convection, we get plumes that might focus on internal forms and have regionalized variation of the composition. And so Mars is just sort of, I would say, a launching point, starting point for trying to think about how we could use this type of seismology elsewhere in the solar system. Earth is one of our most easily accessed planets. Mars, we're going to soon have instrumentation there, but we could think about maybe where we would see other discontinuities in, say, for example, Venus. I mean, Venus is almost the exact same size as Earth, with a totally different thermal history and a totally different evolution of its atmosphere. If plate tectonics or any kind of recycling ever took place on Venus's history, it might be interesting to know if there's still a signature of that in the mantle. So that's just one of the things we could do. So I think I hopefully have convinced you that the Earth is heterogeneous and that possibly we can go and take some of these mechanisms and apply them to elsewhere in the solar system and think about the heterogeneity of the other planets. With that, I'll thank my various characters and individuals who have contributed to this work over time. Of course, my advisor at ASU, Ed Cornero, which is, I love this picture of him. Captures this character very beautifully. And then some of the simulations by Alan and Maxine. And then, of course, collaboration with a whole variety of seismologists and physicists. So I'll leave it at that.
Questions? Kyle.
So you mentioned very early on that there's evidence of subduction of sediments, and presumably some of those sediments would be very silica-rich. So could they also be contributing? Do you have heterogeneous distribution?
I don't see why not. The question is just how much of it is there, and if it gets mixed in a whole bunch or not.
So wouldn't you expect to see, if that's really what's happening, a stronger secondary subduction presumably at lower temperatures, greater depths?
It's a question of maybe how much of that comes back up with the mechanism that brings it back into the mantle. So like if the plume is only getting a little sniff of that, let's say you bring up a fraction of a %, maybe not, but on the other hand, I mean, who knows?
Val.
I actually have a question about some of your introductory material. We might want to go back to the slide where you were showing how much temperature versus composition changes the position of the 660.
Yeah, this one right here?
No, a little forward where you actually showed the Clapeyron slopes.
Oh, right. The interpretation one.
Yeah.
This one
So
right
here and then then in the next one, then next you showed the composition. So I was just wondering, it just looks like from this that the 660 would be not very much affected within reasonable compositional range, but would be very affected by temperature, whereas the 410 is affected strongly both by temperature and composition. So I was wondering if you see anything, if people see anything actually that the 410 changes a lot and the 660 doesn't.
That's a very good question. And in fact, I should point out one thing about this diagram, is this is just for geology.
Okay.
The mantle is actually a mixture of the garnets and the olivine. And actually, at 660 kilometer deep in the Earth, you have that garnet phase transition sort of come into play as well. And so there's an interplay between those two. So it's actually a little bit more complex than this. But your question is a good one. Is do we see more variation on the 410 than the 660? And in the Earth, it's the opposite. We actually see more variation on the 660 than we see on the 410.
Okay.
And this is a whole nother talk, but like one of the reasons we think for that is because of the scale of the upwellings and downwellings across those boundaries. There's a big change in viscosity in the 660. So if you kind of think of a plate, for example, sinking through the mantle, it doesn't really slow down at the 410 very much. There might be some phase transitions in it that can slow it down. But the 660, it might actually lay out and stall there for a little bit. So the signal of it's going to be actually much easier to detect seismically than these sort of really small scale variations that are coming through the 410. So there might be a scale character that changes there, so it might not necessarily be representing the actual Clapeyron slopes and the discontinuity themselves. But there also might be, compositional heterogeneity at the 660. You have a big change in viscosity between materials. It's possible to sequester things there. We'll suggest this from the Farallon plate as it goes through the transition zone in the western U.S.
Rick? There are a couple issues. One is if you have large quantities of basalt in the mantle, you end up with more basalt than the Earth can have convectically.
Yeah.
And the other one is that if you've got quartz-saturated basalt, the first melt of a quartz-saturated basalt is tourmaline, and Hawaii doesn't have tourmalines in it. So, I mean, after subduction processing, subducted basalt is probably silica undersaturated. But if you have 3 quartz in abundance in subducted basalt, it could quit.
Well, I mean, what fractions of percent are we talking about here?
Well, if you have 50% of your rock is basalt, and it's, I mean, I have to know what volume percentage of those big blobs Maxine has are, but you quite rapidly end up with a lot of basalt in the mantle. Cosmically, you can't tolerate it.
He's talking more on the order of like 25 to 30 to 40%, somewhere. It's not quite the high end. He's very cognizant of this issue of having too much basalt. And so the places where we see the really largest fractions of basalt are actually the subduction zones, which that I don't think is problematic because you have basalt essentially going down there. But elsewhere, yeah, I mean, there are some, I can't show them really in an easy to understand way in one of these diagrams. You have to actually look through the stacks. There's some uncertainty on the actual amplitudes as well. So these are sort of the high end number, if you think about sort of the intermediate and then the low end number as well. So there's a lot of variability. But you don't really need a lot of basalt to get this coezine tissue by phase transition to actually show up seismologically.
But you have to have 3 quartz in basalt.
Yes.
I'll make a comment that's it's not necessarily directly related, but one of the most ubiquitous inclusions you see in sublithospheric diamonds is coezite, and it's in half the suite that we've looked at, and it's pretty much ignored by the petrologists because no one's interested in quartz. And Alina Belanova had it in every sublithospheric diamond she looked at, and just ignored it until Andy Thompson, Mike Walter's student, said, hey, there's quartz in every single one, there's coezite in every single one of these diamonds. So we don't know if it's the silica content of a supercritical fluid, that's partly a melt that's giving us that free silica. We don't know how much is there, or whether it's special to the diamond forming regions, but it's there, and you can then make of it what you will. But you're saying you only need 1% or 2%?
Less than 1%.
I mean, you make a very good point, but that's not very much quartz to affect things drastically. I don't know.
I think it's a lot.
You?
No.
Well, I should point out there's perhaps another hypothesis that could be played here too. Because if you look at where the onset of melting takes for carbonatite, it's actually around the same depth. But the thing is that the fraction of melt that you get from like carbonate and carbonatite melting is really, really, really small. So it's hard to find a way to make that into a seismological signature.
Dave?
You focused on ocean basin, younger part of this cycle. What would you expect would be, what remnants would be left in the structure on the continents?
Well, the continents have an interesting dynamical history. They've been frozen in for a very long time. Depends on if you're on the active margin or on the craton. But it's hard to say. I would expect that the signature of this thing, especially if it's coming from some sort of enrichment, might be something that's frozen into the continental space. But We also have sort of the added problem of this is where the base of the lithosphere might fall as well too. So we might have some changes in anisotropy that could overlap. We actually just got funding to work on a project that goes in and investigates these discontinuities underneath the continents here recently, like last week. So I have an answer for you maybe in a year or two.
So you had your hand up.
Yeah. Let me just comment on your modeling for plumes, where you have a plume very nicely leaking out into the shallow, into the transition zone above that. I think you use a static mantle at bottom heating, and if you have in the Earth, it's a very high Rayleigh number, and so when you have a plume, it's surrounded by a very large pipe of lower mantle material, which goes up all the way.
Right.
And you can see the seismological evidence for this from Hawaii, SES on Hawaii, actually should be late with your plume model, but actually it comes in early because the sheath that comes up of lower mantle material is quite high velocity. Now, my question is, what does this affect on the leaking out of the plume? You've got this
Sheet of pipe.
coming up. You know, I think it's worth putting in to see if it will separate.
You know, I think Maxim has a flow field in his model already. I have to check with him on that. I don't know for sure. Because if you look at some of his diagrams, he's showing the sort of flow field around the plume. I'm not sure if that's imposed or if it's something that's primary in front of him.
Right.
But yeah, it's a good point.
Yeah, but with computers now, you can put in a convecting mantle and put the plume in, and you can get the whole thing.
We've been trying to push those models to sort of their limit here. He's got a run running for me right now where we're basically trying to extend the depth of the box that he uses and also incorporate some of those parameters. The real key though is to then say, okay, well, we've got a thermal and compositional field. Let's attack that with some mineral physical model and see if we can actually show what the seismic structure would be if it's consistent with the observations. But yeah, your point is well taken.
Kyle.
Just a thought after Steve's comment. If you have fluids coming off subduction zones that are silica saturated, and then they're metasomatizing mantle above it, and then you recycle that mantle, would that also be a source of silica?
Yeah.
So you might not need to have silica bearing the salt.
Well, the main reason we focus on the hotspots here is this is where you sort of see this really strong enhancement of the discontinuity. It's all downwind. So the suggestion is that it's something to do with the plume itself. But you're right, you do see there's areas away from the plume where you actually have observations as well, where you might have this sort of background effect as well. But I think it's fair to say that the boundary shows up over most of the Pacific. So the question is, why is it locally different?
Any other questions for Nick? Let's thank him again. Thank you very much.